Okay, so last few lectures, we have been building the foundation for deep learning and how neural networks work, how they are trained. And the general idea, if you recall, was we will create some neural network. Okay, it will take on some training data, for example, X. Based on the training data, I will produce some output. In our terminology, whatever output it produces, we were calling it A, short for actual output, right? Then from the training data, see, the training data is always pairs, X and Y. So X is the input and Y is the expected output. So once the neural network produces an output A based on the input X, from the training data, we will also give it Y. Then this will be passed to what we call a loss function. So the loss function will compare what the actual output is with the expected output. Sometimes the expected output is also called the target in the terminology. Okay, so based on how they differ, we will produce one number, which we call the loss, right? So there's always a forward pass in our training of a network where we feed the input data, compute the loss, and then we go backwards, and that's called the back propagation, where we go and adjust the weights and the biases. So this is how we train our neural networks, right? Okay, so the algorithm that we use for going backwards and adjusting the weights and biases is called gradient descent. And just to quickly refresh your memory, the idea was like this. Let's say we have one weight, just one single weight. In the real neural network, we'll have millions of weights or billions of weights these days. So suppose our loss function looks like this, okay? So this is our loss, okay? Meaning there's an ideal value for the weight where the loss will be the lowest possible, right? So this is our goal. How do we find that weight, okay? So in the neural network, the weights are initialized randomly. So initialized randomly. Okay, so which means our starting weight could be over here. So this is our initial weight. Or it could be on the left side, so it doesn't matter. So our gradient descent algorithm, what it does, it keeps adjusting the weight. So the new value of the weight will be the old value of the weight, and then minus, there's some learning rate over here. For example, 0.01, and partial L over partial W, right? So intuitively, we discussed that whenever we do a partial of one output with respect to an input variable, essentially that's measuring the slope, right? So if the slope is this way, the slope is positive, or the derivative is positive. If the slope is this way, then the derivative is, or the slope is negative, right? So the idea is, as you can see, we want to adjust the weight this way, because this way we will get close to the ideal weight, right? So in our example, if we started it over here, you can easily see that this was positive or negative. See at this one, it's the direction is like this, right? So which is positive. So which means the old value of the weight, this is the initial value of the weight, will be subtracted some value based on how the slope is. So the new weight might move over here. So if we keep repeating, hopefully we'll come to the ideal value, right? So that was the fundamental idea behind the gradient descent algorithm, right? Okay, and you can convince yourself, even if we started it somewhere over here, now we want to move the weight this way. So the gradient is negative. So negatives times negative, it will become positive. As you can see, will increase the weight value, and the weight values increase this way. So we'll start to move this way, right? Okay, so then we discussed that if we have a single neuron, sure, our loss function would be easy. Gradient calculations will be easy. Then if you remember in the last couple of lectures, we took a look at 3 neurons, 5 neurons, and we were able to calculate the derivatives. We came up with the delta rule. And the idea in the delta rule, if you remember, was if we have some neurons, every neuron does a summation, then an activation function, a summation, then an activation function, right? Then it goes to another neuron, summation, activation function. Okay, so let's pretend we have a 3 neuron network. Okay, so you, as you know, every input will go to every other neuron, right? Okay, so in this example, suppose we have some target given. And here's our loss, right? So just to refresh our memory on the delta rule, what was the concept over here? Delta was the value of the gradient with respect to the loss up to the middle of the neuron, right? So if we call it neuron 0, then this will be, suppose, delta 0. This will be delta 1. This will be, let's say, delta 2. Right? What's the definition of delta 2? Definition of delta 2 is partial L over. Okay, so again, if we call it S0, A0, S1, A1, S2, A2. So what will be then delta 2? It's the gradient up to the middle of the neuron, right? So this will be partial L over S2, which is same as writing partial L over partial S2, meaning we go for partial L over partial A2. Okay, partial L over partial A2, meaning we go up to here. And then from here, we go up to here, right? Multiplied by partial A2 over partial S2. You can see this will cancel over here. And the left partial L over partial S2 is the same, right? Okay, why do we compute the deltas? Because once we have the deltas, let's say this weight is called W0, W1, W2, W3, W4, W5. Okay, as we discussed, once we know this delta 2, right? Okay, then what if we wanted to know, because in the gradient descent algorithm, every weight, so if it is W4, it will be W4 new value will be updated as W4 old minus lambda partial L over partial W4, right? So if we know delta 2, the question is, what will be partial L over partial W4 in terms of the delta 2? Okay, anybody can figure that out? Okay, so remember, if we take a look at, for example, this S2, right? What will be the value of S2? S2 will be A0W4 plus A1W5 plus B2, right? There will be a bias over here. Let's call it B2. Correct? So now take a look. We already know partial L over partial S2 because that is what the delta 2 is. Like I said, it's the derivative up to the middle of the neuron, right? So now we just need to go one step backwards, which is multiply it by, partial S2 over partial W4, right? Okay, so this is the equation for S2. What if I take the partial with respect to W4? Remember, when we take the partials, all other variables are treated as constant, so the derivative is 0. So what will be the partial S2 over partial W4? A0. So which is basically the input that is feeding via this weight, okay? So in other words, if let me see if everybody's following the concept. Okay, suppose we already have computed delta 0. So what will be then partial L over partial W0 in terms of delta 0? Okay, so remember, as you saw, a partial L over partial W4 was whatever input is feeding to it because it came out to be A0. A0 was the input feeding to the neuron via W4, right? So then similarly, you can see partial L over partial W0. What's the input that's feeding X0? So this will be simply multiplied by X0. Okay, so in general, suppose I gave you a neural network, okay, and suppose I have some W9, okay, suppose this output is called P, okay, instead of A, B, C, D, let me just call it P, okay. So my question is, if this delta is given to you, then what is partial L over partial W9 for this picture? Delta times P, which is the input, right? Okay, so now that we understand how all the derivatives can be calculated, right? It doesn't matter whether we have 5 weights and 3 biases or 9 weights. We can write many equations to implement the gradient descent algorithm like you see over here. So if you have 6 weights, this will be 6 copies of this, one for W0, one for W1, and so on, right? Same way, if we have biases, it will be as many bias equations, right? So as we go along, part of our learning is trying to be comfortable with math and also the terminology, because as we take a look at research papers, they will be writing all the equations in a very compact way. So as I mentioned to you in one of the previous lectures, rather than writing this type of equation for every weight and every bias, what we do is we describe the gradient descent algorithm as theta equal to theta minus lambda partial L over partial theta. Okay, so this is one line math description of the gradient descent algorithm. So what is theta? Theta is basically all the weights and biases in our network. So this is a compact way of describing what the algorithm is going to do. For every weight and bias, is going to compute the gradient and subtract. And we repeat this many times until the theta does not change, until the weights and biases have reached a stable value, right? Sometimes you will see as we train a network, it just keeps changing. So the question is, when do we stop? Okay, We just keep running it into this loop, and it keeps giving us a slightly lower and lower weight value and so on. So there's a concept that we will clarify today, and it's called overfitting. So it's a very important concept. Okay, so when we train a neural network, okay, we do not want it to overfit. So what do we mean by overfit? And how do we know that it is overfitting? So basically, too much training will cause overfitting. So that's a general rule. Okay. So you don't want to train it too many times in that loop. Okay. Further, more data we have, okay, the less is the chance of overfitting. So these are neural network rules that you should remember. Okay. So data is very important. If you recall in the beginning of the course, if somebody says, what is AI? Okay. My definition of AI is it can learn a mathematical function describing the data from the data. Okay. So the more data we have, the better it will come up with the approximation for describing the data, right? Okay, so we are always looking for as much data as we can get, then the model we create will be a lot better as opposed to something where we don't have much data, right? Less data will cause overfitting. So let me first show you pictures. We talked about it a little bit, but I didn't show you a good picture last time. So let me show you a good picture first to clarify what is overfitting. Then we'll take a look at the techniques to prevent overfitting. Okay, so if this is the same program I showed you, but I think I have a slight error in the program I showed you. So I went to one of my old copies so that I can at least show you, and I'll fix the error. Okay. So if you remember, this was our goal, right? We want to have our neural network learn to separate the blue dots from the red dots. So you can see a straight line will not separate them. It has to learn some sophisticated curve separating the two types of data, right? We are given 200 points in this example. Okay, we randomly created through a data set called Moon. So anyway, if we train this network, actually, let me do this. First, let me pick less neurons. Okay, so this way we can refresh our memory on this as well. So if we pick one neuron, okay, if you guys remember, we discussed that if a single neuron cannot learn a nonlinear decision boundary, right? So if I pick one neuron in the hidden layer, it's always a straight line, right? And the accuracy, as we discussed, came out to be 86.5. Okay, if we pick, let's say, 3 neurons. You guys saw this last time also, but let me quickly refresh everybody's memory, then we'll take a look at. So with 3 neurons, you'll see it will be able to learn decision boundary a little bit better. And the accuracy goes to 97.5, okay? So the question is, what if we use 30 neurons, okay? So as we are increasing the number of neurons, okay, so from overfitting point of view. Okay. So the question is more neurons better or less neurons better? So more neurons basically means we are making the model more complex. Right? Because it can learn a higher degree or a more nonlinear type of decision boundary it can learn, right? If we have more complex model, we need either more training data for it to be able to at least do a good job. If we do not have more data, we do not have more training data, then this will cause overfitting. And let me demonstrate it to you. So our data is same as 200, right? So so now I've changed it to 30 neurons, right? So if we test it, so obviously it takes a little bit longer to train. So take a look at the decision boundary now, okay? So this is an example of overfitting, okay? And the reason we are saying overfitting is there was some blue dot over here where my mouse is towards this peak over here, right? So what it's trying to do is it's trying to accommodate each and every training data. What if that training data, this blue dot in the over here, was a noisy data, meaning there was an error in the measurement? So that's not real representation of our normal data, right? So we shouldn't be accommodating every noising data in the training. So that's what happens if we pick too many neurons or pick too complex of a model, it starts to overfit. Okay, so what is the disadvantage of overfitting? Let's say somebody gives us, we draw it over here. So the decision boundary you can see was coming out like this, right? Something like this. So here were the okay, at the bottom is the blue dot. So this is the blue region, this is the red region, right? Okay, so remember one of the training data was over here. So the model tried to accommodate that. Okay, what if somebody gives us, for example, a red dot over here? This is now unseen data. So somebody gives us XY coordinate of this. As you can see, if this is where the unseen data was given to us, in reality, should it be classified as red or blue? See, if it was a smooth boundary, right, then you can see most likely our data boundary is like over here. Okay, but because of that noisy data, it created this extra peak over there. So this unseen data, as you can see in the overfitted model, will be classified as red, which is wrong. It should be it will be classified as blue, because remember it is going like this. So anything over here is, according to this, belongs to the blue category. So what I'm trying to say is overfitting will cause proper data to be misclassified, meaning proper data, which is unseen data. Because see, what we do is we train the network, then we use it in real scenario where we haven't seen that data before. Another way to understand overfitting is, I think I gave an example of it. So what if our data look like this? Okay. And suppose it can be okay, it can be separated by a straight line. Okay, but due to some measurement error, if we pick too many neurons, it will try to accommodate each and every neuron. So it's like, if the model is basically a straight line mathematical model, but now you are saying, no, I'll pick a fifth degree polynomial. Sure, for the training data, if this is the training data, I will do a great job. But for unseen data, I will not do a good job. Okay. Okay. So one of the challenges is for, I mean, these are simpler examples. In more complex examples, how do we know that the model is overfitting and we should stop the training? Like I said, even if we train it too many times, it again tries to accommodate each and every training data and creates a boundary which is trying to accommodate each and every data, right? So as we go along, what you will see is, so the question is how to prevent overfitting. Okay, if we plot the loss as a function of the training, remember training loop? Okay, the training loop, let's say will go 10 times, 20 times, right? And somewhere here is, let's say, 1,000 times, right? If we try to plot the loss, typically what happens is in the beginning, the loss is high. And then as the training keeps going, it keeps decreasing. Okay, so the training loss, and that's what I'm saying. If you'll say, oh, the loss is decreasing, let me keep training, right? But at some point in time, we don't know where. Let's pretend over here the model is proper, and if we keep training it more, then this is where we will end up with an overfitted model, which will do a good job on the training data, but poor job on the unseen data, okay, or the test data. Okay, so how do we determine this point? Okay, and the answer is, what we typically do is we use three types of data. We divide our data set into training data, test data, which we will not give to the model, and validation data. Okay. So for example, we may decide, okay, we will use, let's say, 80% of the data for training. Okay. We will keep 10% of the data for testing, meaning we will not provide this data to the model. And 10% also we will not provide. We call it validation. So what we will do is, for example, we'll train it 10 times. So train 10 times. Okay, then validate one time. And compute the validation loss, meaning how good of a job did it do on this validation data. Okay, so if we plot the, and we keep doing this procedure hundreds of times or 50 times, or let's say we wanted to go up to 1,000, right? What you will observe is, in most cases, the validation loss will also start to decrease. Okay. at some point in time, what will happen is the validation loss will start to increase or become flatter, okay? Which means, remember, validation also is not being used in training. It's just being used to verify how good it is doing on the unseen data. So wherever that crossing point is, that is when we should stop training. That model will be the best model. Okay, so this is a typical technique we use in training neural networks. So to summarize, what I'm saying is just keep training it. More and more is a bad idea. Okay, you should stop the training once the validation loss starts to reverse. Okay. The other thing to remember is the more training data we have, the better the model will be trained. Okay. Still, how many neurons we should pick? The number of neurons is dependent upon the complexity of the model. Okay. Or complexity of, let's say, decision boundary. For example, if you already know the data is linearly separable, there's no need to pick more than one neuron. Okay. If you know the decision boundary maybe have two curves like this, 3 neurons may be enough. Okay. But as we go into more complex problems, okay, for example, if you take a look at ChatGPT, the first ChatGPT had 175 billion training parameters. If we call each weight one training parameter, so you can see it is a huge model, right? Okay, if we did not train it, if we trained it on a small amount of data, such a complex model, what will happen? It will overfit. Okay, it may do a decent job. Think of overfitting. Maybe another good way to understand overfitting is like memorization. To give you an example, let's say you were learning math. Okay, for example, you memorize 1.5 times 1.5 is 2.25. You memorized it. Okay. Similarly, let's say 2 times 2 you memorized is 4. Okay. So if all your training data was like 3 times 3 or 1.2 multiplied by 1.2 is 1.44. Okay. So you did a great job in memorizing all of this. Okay. Now you go to take an exam, and the question given to you is, what is 1.3 times 1.3? Let's pretend this was not part of the training data. So now you will give a wrong answer because it's not in your memory. So training it too many times is same thing as it's trying to memorize the training data rather than trying to learn the in the technical terminology we call it generalization. So we want the model to be able to generalize, meaning to be able to predict correctly on unknown data, right? Okay, so coming to how do we prevent overfitting is a very, very important part of AI. Okay, you can, so now let me give you 3 techniques to prevent overfitting. Okay, one, use a model that is or that has complexity corresponding to the nature of the problem. And like I said, if it is linearly separable, just use one neuron. If it is maybe 100 neurons will do the job, use 100 neurons. Don't put 1,000 neurons where 100 neurons will do a good job, right? Second is use more data. Okay, more training data. That will always make the model better as opposed to using less data. Because if it has less data, we'll try to accommodate that all that less data and memorize that data. But when you have a lot of data, it has to figure out with the limited number of neurons it has, how it can accommodate all that large data. So it tends to come up with a decision boundary, which is not memorizing all this huge data, but trying to see what are the general patterns so that it can do a decent job over the whole data, right? So the third technique is called regularization. Okay, so this is used as part of the training. Used as part of training. Okay, so one of them is like the weight regularization. So one technique is called weight regularization, and one technique is called dropout. Both of them are fairly easy techniques. Okay, in the weight regularization, okay, so suppose our loss function, I'll pick an easy example. Our loss function is, let's say, y minus a squared, right? And as we discussed, we typically put 0.5 over here. Okay, we will now try to try to implement this like W minus lambda partial L over partial W, right? For all the weights in our network. So this such that this loss, which is the mean squared error, keeps getting less, right? Okay, so what we found out that to give you an example, right? So let's say you have a input is 0.2, right? Another input is, let's say, 0.1. Okay, what happens if we train the network and these weights, let's say W0, W1, are very large? Okay, the training algorithm, as we apply this W equal to W minus lambda partial L over partial W, let's pretend it gives us weights like 57.2. This comes out to be, let's say, 92.7, right? So when these are large, you can see, what if somebody gave an input of 1.2 instead of 0.2? Now it will produce huge numbers, okay? So in a neural network, through our all of our extensive studies, what we found is that large weights result in poor model. Once again, poor model is the one which does a poor job on test data. Okay, it may still do a decent job on the training data, but for the unknown data, I will do a poor job. So the goal of the regularization is, because we know we cannot have large weights, so we want to minimize the loss. So if I put it in plain English, goal of regularization is minimize loss by selecting weights that are as small as possible. Okay, so in plain English, that's the regularization technique. Okay, so the question is, how do we accomplish this if this is the goal? Okay, and the answer is, just like why did we put this? What is y over here? Target. What is a? Actual, right? So as we keep applying this W equal to W minus lambda partial L over partial W, what is the model doing with respect to Y and A? It's trying to come up with those weights which will make the actual same as the target. Because then if they are equal, what happens to the loss? Loss becomes zero, right? So now we still want to accomplish this in regularization, but we want to accomplish this such that whatever weights it came up with, which make these two equal, are also very small. They're not large. So what if I do this? I add W square over here in the loss function, okay? So take a look, what's the goal of the neural network? Goal of the training of the neural network is to make this loss as big or as small as possible. As small as possible. If A is very close to Y, then will the loss be less? Yes. What about the weights? If the weights are very high, will the loss be less? No. So if this is the loss function, and as we compute the partial L over partial W, you can easily see both terms have to be as small as possible for the loss to be less, which means A has to be equal to Y, which is our goal anyway. But the weights also have to be small, otherwise it will become, right? So this is what we do to the loss function. So how does this change the gradient descent algorithm? So let's go and compute this partial L over partial W. So you can see what will happen. W equal to W minus lambda. Okay. Partial L over partial W. So we will do the derivative of this. Okay. So let me, whatever that derivative is, what about this? As we compute partial L over partial W, what will be the answer? If I say L is W squared, what is partial L over partial W? 2W. What if in the, just like I put a 0.5 over here so that we can have an easy 2 and 0.5 can cancel. Let me put 0.5 over here. Then what will happen? It will just become W. Okay. So what I'm trying to say is, let's go to our one of our examples that we did earlier, right? Okay, let's take a look at, for example, in our training loop, we were updating W4, right? So as we are going into the loop, how will W4 will be updated? Equal to W4 old minus partial L over partial W4. Now let me add the regularization to it. Then what will happen? Plus W4. Because remember, the goal is to make it weight each as small as possible. And once again, you can go over here, right? So like I said, as we try to minimize this, right? This loss, because we'll be taking the derivative of this term, okay? And we'll also be taking the derivative of this term, okay? See in math, if I gave you, for example, let's say I gave you z equal to 2x cubed minus 6x squared, right? So if I asked you partial z over partial x, won't you take the derivative of this term, then derivative of this term, and just add the two? So what will this be? 6x squared minus 12x, correct? So what I'm trying to say is, as we go over here, because in the loss function, we added this w squared term so that smaller w will give us the lowest, I mean, the loss will be low when the w is small. So if the 0.5 w squared was added, then we will do the normal derivative of the first term. So this is what we were already doing, okay? So what will get added then? Plus W will get added, okay? So that's what we will add to everything. And now the end result will be the neural network that we train will be less susceptible to overfitting, okay? So remember, the job of the regularization, or the purpose, is to prevent overfitting. Hey, so this is one way we try to accomplish that, by coming up with weights, which still reduce the loss, but the weights themselves are as small as possible, okay? The other technique that we will use is called a dropout. So dropout is an extremely easy technique. So let's say we have a neural network. And normally, like I said, we'll be using 2-layer network. But even if it is more layer network, keep in mind dropout is never applied to the output layer. Okay. And dropout basically zeroes out the output of a neuron. And in dropout, neurons are selected randomly during training. Okay, during testing, we remove the dropout. Okay. So for example, let's make it 5 neurons in our example. Okay. So as we feed in some input X, right? Suppose there are 3 outputs. Like I said, these we will not touch. Okay. Whatever output they produce, we'll let them produce. It will go to the loss function. And whatever the 3 target values are. Okay, so these are kept as is. However, these 5 in our example, which are feeding to each and every neuron. Okay, let me use a different color. So And similarly, let me use a different color. Oops, sorry. This should be going here. This should be going here. Anyway, okay. So we have these 15 weights going over there, right? So what we will do is during training, in our training loop over here. Okay, for example, we'll pick, let's say, we'll pick dropout rate of 20%. Okay, so we always select like percentage of neurons that we will zero out, whose outputs will be zeroed out, okay, randomly during training. So if I have 5 neurons, as you can see in my model over here, in the hidden layer, I have 5 neurons. What is 20% of 5? 1, right? Okay. So that means I'll pick one of these neurons and I'll zero out their value. Okay. So let's say I select this neuron. Let's say I select this neuron. Okay. So suppose this is producing an output of 2.21, 0.17. Let's say the output over here was minus 0.3, 0.01, and whatever, negative 0.02. Okay. So suppose at some point in time, these were the 5 outputs based on the input data, right? As we do the forward pass. So if we said, oh, use a dropout of 20% during training, we'll throw a random number between 1 and 5. Let's suppose it lands 3. That means this, in the calculation of the outputs, normally this negative 0.3 will be used. Now we will say wherever it's feeding to, that zero it out. Okay, as if this neuron was never there. So now, as you can see, as we go to the forward pass and then go backwards, we are trying to compensate for lack of this neuron, as if this neuron was never there. So in other words, think of it this way: the 4 neurons are trying to learn the same thing as 5 would. Okay. To give you an example, if you're, let's say you are in a soccer match, okay, remember they give you yellow card and red card. So suppose one of your players was given a red card, that player is not there. So now the 10 players have to learn how to be still an effective team. So that is the dropout. Okay, dropout is like red card for a neuron. Okay, and we randomly pick. So in the next part of the training loop, again, we'll throw a random number. And this time, who knows, we may zero out this one and keep the others. Okay. So the idea is the other neurons learn how to compensate for the missing neuron. As a result, the model that we come up with is less overfitted model. It generalizes a lot better to the unknown or the test data. Okay, so dropout. So let's say you created a model. And remember, we do train, test, validation. Okay, suppose it does a great job on training, okay, but does a poor job on test data, okay? You can, most of the time, make that better by increasing, if you were not using dropout, start out with a 5% dropout, see how does that affect the test data, because that is our everything we do, we want to have it do a great job on the test data. Other things are less important. Okay. Of course, if it's not doing a good job on training, it will do a guaranteed terrible job on test data. So you may start out with a dropout of 5%, 10%, 15%. Sometimes people even use 50% dropout, but that is rare. Typically, 10% dropout is pretty decent for most of the things that I've worked on, and it does a great job. Okay. So to summarize then, two important things we covered were, one was overfitting needs to be avoided, should be avoided as we create a model. So don't pick too complex of a model. Don't pick too simple of a model. There has to be, like the Goldilocks story, just right. Okay. So once you have just right, then use regularization. Okay, and that adds plus W squared term to the loss function. And all it does it, because the derivative of W squared is 2W, and if I put 0.5 over here, it's just W. That means during the training process, keeps adding W, right? Let me show you a code and see if you can recognize it right away. Okay, so in this case, this is the same where we were using 3-neuron, the red blue dot problem. Okay, so let's take a look over here. DW. Okay, where did I put it? Let me try to see, where did I put it? Maybe it was in another example. Yeah, maybe it was a different example. Okay, so I'll show you the use of the dropout and regularization. Okay, so now let me come to clarify one more time, because some of the students stopped by and were a little uncomfortable with the softmax loss and the cross entropy loss that we talked about last time. So let me quickly go over that. So let's pick the example of this 3-neuron 2-output problem. So same, we have the red blue dot example. Okay, so let me quickly create this and we'll go over the equation so that everybody understands it. So let's say, okay, we have 3 neurons. And remember, in our example, we had 2 inputs, x0, x1. These are the xy coordinates of a point. Okay, whether, so if over here, if the point, whatever the x is, we were calling it x0. Whatever the y coordinate is, we're calling it x1. So then it could be a blue dot or red dot. So we will feed the XY coordinate. We already know in the training data if it's blue or red. So the red, suppose, is 1. and blue will produce an output of 0. Okay, so we have 1, 0. So we will have two outputs. Let's say the top output is for red, bottom output is blue. So if the neural network produces 1 and 0, what is it recognizing? As a red. Okay, if it, on the other hand, produces 0 and 1, then it is recognizing it as a blue dot, right? If we draw our architecture, right? This is X0, this is X1, okay, and now we need two neurons over here, two neurons on the output, okay, and here will be our loss function. Okay, so let's start from the input side. As we discussed, every neuron goes to, every input goes to every neuron, right? So then this will be like this. And there will be B0, B1, and B2, right? And similarly, this will go and similarly, this will go. Okay, so this is our network, right? So last time we also discussed that as we start putting more and more neurons, we want to come up with matrix form of equations such that depending upon how many neurons we have, we don't have to write a separate equation for each and every neuron, right? So let me see if you guys see this very clearly. So let's start. Suppose how many weights will be involved on the input side? 2 inputs, 3 neurons, 2 times 3 is 6, right? So last time, remember, we came up with a philosophy. When we write a weight, what will we put first? The output number or the neuron number, followed by input number. So what should I call this weight over here? Okay, see, pretend this is neuron 0, this is neuron 1, this is neuron 2. Okay, so we start with the output 0, and it's coming from input X0, so this should be W00. What about this one? Output first, 0, 1, right? Because it's neuron 0, and the input is coming from 1, so it will be 0, 1. How about this one? Neuron 1, input coming from 0. Neuron 1, input coming from 1, right? This is 1. And you get the idea. 2, neuron is 2, input from 0. Neuron is 2, input from 1, right? So let's write the equation for S0, S1, and S2. So if we write the equation for S0, what will this be? Okay, this will be W00 times X0, right? These two are being multiplied, plus W01 times X1 plus B0, right? Similarly, let's write S1. Okay, W10 is going to X0. It doesn't matter whether I write X first or W first. These are numbers anyway. W10 times X0 plus W11 times X1 plus B1, right? S2, let's go to W20. x0 plus w21, x1 plus b2. Okay. So once we write this, now you will see that this could easily be written as a vector and matrix. So if I assemble this into a vector, S0, S1, S2, if I assemble all the weights into a matrix, and then x0, x1, and all these b0, b1, b2 as a vector, okay? And you can verify that this matrix equation that I wrote over here is exactly the same as these three equations, because if you expand it, remember in matrix by vector multiplication, what is the size of this matrix? We always go rows by columns, 3 rows, 2 columns. So then what is the size of X matrix? 2 by 1. These have to be match in matrix multiplication, otherwise we cannot multiply. So what will be the answer as we multiply 3 by 2 with 2 by 1? It will be 3 by 1. So then we can add it with 3 by 1. So you can see, and the answer will be 3 by 1, and you can see the left is 3 by 1, right? And the way matrix multiplication works is row gets multiplied by the column. So you can verify that from this matrix equation, S0 is exactly W00 X0 plus W01 X1 plus B0 over here, which is same as equation 1, right? So now rather than writing an individual element, what if I call this vector S? What if I call this matrix as W1? Okay. Reason I'm calling W1 is because I have one more weight matrix over here, which will be corresponding to these weights over here. So let me call the first one as W1, right? So as a matrix equation, can't I write S equal to W1 times X plus B? Okay. Or let me call it B1. Okay. Now, this S is representing the three S0s, S1, S2, right? They will pass through some activation function. And let me call that activation as A0, A1, A2. So as you can see, and if I assemble them into A1, so this will be basically activation as applied to the S in our examples, right? Okay, so similarly, so what's the size of W1 in our example? 3 by 2. What's the size of this? 2 by 1, and this is 3 by 1. Okay, so what I'm trying to say is we can express all this information going through the first layer as one matrix equation, which we just said is W1 X plus B1. And then we'll pass all of this to the activation and we'll produce over here, we are calling it A1 as an example, as a vector, even though, so if I make it bold so that you don't get it confused, this A1 is not this A1, it is the assembly of all the column of A's as a vector. So similarly, this B1 is not this B. Usually what we do is if it's a vector, we'll put it in bold in math. If it is a single variable, we won't put it in, right? So X, sorry, this is no x1. X is just the input. So this is what the equation will be, W1 x plus B1. And then A1 will be the activation applied to this S1 over here as a bold, will be, right? So very similarly, rather than me writing it, can you tell me if I call it W2 matrix, what will be the size of this? See, this W1 that we created was 3 by 2. So think about this way. What was 3 over here? 3 was the size of the output side, right? X is the input side. The 3 is the neuron, which with respect to the weight is the output side. So, and the reason it was 3 by 2 is because our terminology was what? First, we write the output index, then the input index, right? So hopefully now you can tell me what should be the size of this. How many things on the output side? 2 neurons, right? How many on the input side? 3. So it will be 2 by 3. Okay. Can you now give me the equation if I call this S2? What will be the equation in terms of this A1 over here? Because A1 is feeding as a vector to the second layer. So you can see this will be W2 times A1. So let's see if the sizes match, okay? Because as we write the code, you cannot multiply matrices if the input dimensions do not match. So what is the size of W2 we just decided? 2 by 3, right? So what should be, what was the size of A1? Take a look over here. 3 by 1. So this is 3 by 1. Do these match? So plus, suppose this is the vector B2. B2 are these biases. Okay, so there are 2 biases, so this will be 2 by 1. So does this satisfy? Will this part, what answer will it produce? 2 by 3 by 3 by 1, right? Remember, inner dimensions disappear. Answer will be 2 by 1. 2 by 1 plus 2 by 1. And you can easily see there are 2 S values. So this is our forward equation for the second layer, okay? Similarly, we can go over here and so I'll give you a short break. After the break, what I want to show you is what if this is our loss over here is cross entropy, and when do we use cross entropy, and how will it be calculated so that we can write the code and right? So once you feel comfortable with one of these calculations, then, you know, we don't have to go into this much detail next time. We can view it as, for example, if I give you a model and I say the input coming in is 500 by 1, okay, what if we are using 100 neurons over here? Okay, now can you tell me what will be the weight matrix very quickly? 100 by, because we go by the output side, then the input side, okay? Do we have to go output side, input side? No, we could have done the other way as well. But as long as we are consistent, then as you will see, we won't have any confusion. Matrix dimensions will match correctly. The code we write will become very easy to follow. So all of our calculations will be done at the matrix level. Doesn't matter whether we have 500 neurons or 10,000 neurons. So you'll see things will become a lot easier. So let's take a short break and we'll continue from here. Hey, so before the break, we looked at the review of how do we set up the matrix equations for feeding the data through the neural network, right? And the general philosophy, or I should say the terminology that we were following was that anytime we put a weight, we start with the number of outputs and followed by the number of inputs. So as a quick check, suppose you were creating a neural network. Hey, with quite a few layers. Let's pretend over here we have, let's say, 300 neurons. Suppose over here we have 200 neurons. So obviously there will be a weight matrix involved connecting the 300 outputs to the 200 neurons over here. Each one of these 300 will be going to each and every neuron over here. So my question is, what will be the size of this weight matrix? What was it? 200 by 300. Yeah, so whatever is on the output side, then the input side. Then, like I said, our math becomes a lot easier. We can write, for example, if this is, let's say, out, and suppose this, we call it, let's say, A2 as an example, right? So then out will become A2 times, sorry, WA2 plus B2, whatever the B. So W will be 200 by 300, and A2, if it is coming from the 300, you will see will be 300 by 1, and this will match, and everything will work out properly, right? Okay, so next thing I wanted to clarify was the cross entropy loss. So as we go along, we will come across different loss functions. We had briefly talked about it in the last lecture also. For example, there's a mean absolute error, there's a mean squared error, there's cross entropy, there's the contrastive loss, and we'll come up with our own special loss function. So anyway, there are many, many loss functions. Depending upon the nature of the problem, we will pick one of these loss functions, right? And as we discussed, if this is our neural network, whatever the outputs are being produced, they are, sorry, these will be coming from our target, not from here. Okay, and we'll go into a loss function. And this loss function could be any one of these. And so depending upon the loss function as we go backwards, you'll see the gradients will be affected. For example, if it is mean squared error, then the gradient from here to the actual output becomes easier. For example, if it is y minus a square is our loss, then partial L over partial A becomes simply minus y minus A, correct? Okay, but what if it is cross entropy? Or when do we use cross entropy? Mean absolute is where we take the absolute error between y and A. If it is negative, we'll make it positive, right? Cross entropy is a very popular loss function. So through our lot of research that we have done over the years, we have determined that cross entropy works best for classification problems. So anytime we are trying to categorize the data, then cross entropy loss is the best loss function from the learning of the network point of view, right? Okay, so what was the formula for the cross entropy? The cross entropy formula is negative sum over all the outputs. So these are over all the outputs, yi log of ai. Okay. So to give you an example, so that you understand what this means, suppose there are 3 outputs. Okay, suppose there are 3 outputs, which means there will be 3 target values. Okay, suppose the outputs are at some point in time, 0.2, 0.7, 0.1. Okay, let's pretend it's like this. Let's pretend they went through a softmax function so that the sum of these is 1, right? And suppose this is our target, right? Suppose the target happens to be 0, 1, 1, okay, for a given problem. So the question is, what will be the loss in this example? So the loss will sum over all the outputs. So you can see there are 3 outputs. So for the first one, y is, remember, our target. This is our target. So this will become minus 0 times what's the corresponding actual output. So these are our actual outputs. So 0 times 0.2, right? Plus this symbol, remember, in math means we are summing it. Okay. Next output, the target is 1. So yi will be 1 multiplied by, oh, sorry, this will be log of 0.2. So this will be log of 0.7. So this is log to the base e, okay, not log to the base 10. Okay, similarly, plus third output expected target is 1 times log of 0.1. So whatever that number comes, that will be our loss. So this is how we calculate the cross entropy loss. Okay. So as we discussed in the previous lecture, our typical network, neural network scenario is like this. We may have different layers. Okay, in the very last layer, the number of outputs is decided by the number of categories or the number of classes, right? And the activation function that we use in the very last layer, this activation in our last layer, if it is a classification type of problem, this will be the cross entropy. Sorry, not cross entropy, softmax. Activation is softmax. The loss will be cross entropy. So let's put it together for our simple previous example where we had 3 neurons and 2 neurons in the output, and see how do the equations come out, okay? So we will now create the scenario. Again, the same red-blue example. Okay, so let's make it. Okay, so, and there are some neurons in the previous, right? So remember, we had 3 neurons over here. We won't worry about those. Okay. Our goal is that over here is our loss function. And this is our cross entropy now. Okay. So let's say, to make it easy for us to understand, let me call this lowercase s0. Let me call this lowercase s1. Let me call this lowercase a0 and lowercase a1. Okay. Now remember, this will be a softmax function, right? So now this is going to be softmax. Okay. Softmax does not operate on one input. Okay. As we discussed, suppose we are doing a softmax. Suppose there are 3 inputs. At some point in time, the values are 2, 1, and 7, or 2, 1, and let's say 4. Because before the softmax, the sum will not be 1. Okay. So what is softmax going to produce? If there are 3 inputs, it will produce 3 outputs. Okay. Those 3 outputs will be such that if we add them up, answer will be 1. So we often say softmax turns the input data into a probability distribution. Any probability distribution, the sum is always 1. Okay. So what was the formula in softmax? It will do e raised power 2 over e raised power 2 plus e raised power 1 plus e raised power 4 will be the first output. The second output will be e raised power 1 over e raised power 2 plus e raised power 1 plus e raised power 4. Right? What will be the last output? E raised power 4 over e raised power 2 plus e raised power 1 plus e raised power 4. So this is what the softmax will do, right? So in our example, think of it this way: this softmax. So it's hard to draw it like this in this example, because, for example, the first output coming out of the softmax. So if maybe what you can do is, if I draw a dotted box over here, that is acting as the softmax with 2 inputs going in, 2 outputs coming out of it. Okay. So what I'm trying to say is that the first output coming out of the softmax function also needs this S1 over here. So this S1 will also need to go over here. Okay. Similarly, this S0 will also need to go into the input of this. Okay. Rather than calling it, let me call it, instead of A0, let me call it capital S0. Let me call it capital S1. Okay, because this way, whatever we developed in the previous lecture will match. Okay, so let's take a look at from S equation point of view. S0 will be, there are 2 inputs now to this, right? One is the lowercase S0, the other is the lowercase S1. So you can see the first output will be e raised power S0 over e raised power S0 plus e raised power S1. Okay, very similarly, what will be S1? E raised power S1 S0 plus e raised power S1, right? Okay. So what we want to do is we want to compute delta 0 and delta 1. If we can compute that, then rest of the back propagation will be extremely easy because we can express it in terms of the deltas. So the question is, if this loss is cross entropy, then how is, so let me write the function for the loss function. So the cross entropy loss will be minus, there are 2 targets, right? Y0 log of S0 minus Y1 log of S1. Right? Because remember, the formula was minus summation for the loss function y of I log of A of I. A of I is really capital S0, capital S1 in our example, right? So let's try to compute delta 0, see if we can do it nicely. Okay. Delta zero, if you take a look, is basically from this loss. So let me use a color. From this loss, where will we go back? To capital S0. Then capital S0 to lowercase s0. Because that's where the delta is, right? It's the gradient up to the middle of the neuron. Okay. Now, we also talked about in the previous lecture, if there are multiple paths, then we have to add all the gradients for the different paths. Is this the only way to go from loss to lowercase s0? No, there's another way. And what is that? Go from here to S1, right? From S1, take a look here. I can go here, right? From S1, I can go to S0, okay? So if I write that in terms of the derivatives, what will that be? That will be partial L over partial S0 multiplied by partial S0 over partial lowercase s0, correct? This cancels. So this is the top path, top blue path. What about the bottom path? Partial L over partial S1, and then multiplied by partial S0, right? Okay. So now let's put detail over here. Okay, what is partial L over partial S0? Okay, so let's go to this equation and try to compute the partial L with respect to partial S0. What will happen to the second term? There's no S0 over here. So in partial derivatives, if there's no S0, that will zero out. And remember what is the derivative of the log? 1 over whatever that quantity is, right? So if I gave you z equal to log of x, what I'm saying is partial z over partial x is 1 over x. That's the standard math. So what will be the answer for this term? If you do partial L over partial S0, okay, it will be 1 over S0, which means it will be minus y0 over S0, correct? Now let's go to the second term. Second term is S0 with respect to lowercase s0. So which equation will I use to compute this? This one, right? S0 with respect to S0, okay? So you can think of this as U over V. Remember, if I take the derivative of U over V, it is V U prime minus U V prime over V squared, okay? So let's do this. What is V in our example? V is the bottom part. E raised power S0 plus E raised power S1. U prime, okay? U prime is the top part. And what are we taking the derivative with respect to? S0. So what is the derivative of E raised power S0 with respect to S0? Remember, if you are given Z equal to E raised power X, and if I say what is partial Z over partial X, it is same as E raised power X. So what I'm trying to say is this partial, the U prime, which is the partial with respect to S0, is simply E raised power S0, right? Now let's go to the second term over here, U. U is E raised power S0. V prime. V is the bottom part. What are we taking the derivative of the bottom part with respect to what? remember we are doing partial with respect to S0. So e raised power S1 will disappear and the answer will be S0 divided by e raised power S0 plus e raised power S1 squared. So that is partial S0 over. Okay, let's simplify it a little bit. Okay, let's simplify it a little bit. So I can write this as, see, one of these will cancel with the square, right? So this will come out as e raised power S0 over e raised power S0 plus e raised power S1, okay? Minus, okay? I can write it as e raised power S0 over e raised power S0 plus e raised power S1. And if I split it in two parts, I can do e raised power S0. And similarly, the square, I can split it in two parts, S0 plus S1. Okay, so by definition, what is this? This is S0 minus, what is this? S0, S0, right? Okay, so now let's put this over here. This becomes S0 minus S0 square. Okay, so this becomes minus Y0 over S0. If I take S0 common, 1 minus S0. So S0, S0 cancels. This becomes minus Y0 minus Y0 plus, yes. So these two parts come out to be this one, right? Okay. Now let's do the second part. And even though there are a lot of steps, like as I showed you in the last lecture, the final answer is amazingly simple. Okay. So now let's do partial. So now let's go to the second part over here. Partial L over partial S1. So here's the loss. So now you can see the first term will disappear. Only we'll focus on this one. So what is that? Minus Y1 over S1, right? Now let's go to the second part, which is partial S1 over lowercase S0. So we will now focus on this equation. Okay, so again, let's treat it U over V. So what is V over here? V is e raised power S0 plus e raised power S1 multiplied by U prime. Okay, U is e raised power S1, right here? Okay, but now we are taking the derivative with respect to S0. So what will happen to that derivative? It will be 0, right? Then let's go to the minus. Minus U. U is e raised power S1. Okay, V prime. So take a look at the bottom. And what are we taking the derivative with respect to for the bottom part? S0. So S0, only this term will stay. So this will be e raised power S0, right? Divided by e raised power S0 plus e raised power S1 squared. Okay, the zero zeroes it out. And if you take a look at minus e to the S1, if I split it out, right, in two parts, this is really equal to e raised power S1 over e raised power S0 plus e raised power S1 is simply S1. Then if I focus on the second part and split the square again so that it just e raised power S0 over e raised power S0 plus, so that is just S0, okay? And of course, there's a minus sign there. Okay, so what I'm trying to say is this part turns out to be minus S1, S0, okay? So now what will happen? This S1 cancels. Minus minus becomes plus. So you can see this will become Y1, S0, right? Now let's further focus on it, minus Y0 plus, if I take S0 common, Y0 plus Y1, okay? In a classification problem, okay, so in a classification problem, okay, let's say you have a neural network with 3 outputs, okay? Which means we are trying to recognize which category or class it belongs to, right? What does that mean? If the actual output is 0.2, 0.1, 0.7, whichever is the highest, that's the category the neural network is recognizing, right? So if there are 3 outputs, how many targets will there be? 3. So the target will be such that only one of them is 1. It will never be the case where more than one. We will not say, oh, it's a dog as well as a cat. If we are trying to recognize a dog and a cat and a pigeon, it's one of the 3 categories, okay? So what I'm trying to say is whenever we add all the targets, what will be the answer? It will always be 1 in a classification problem, okay? So this is guaranteed to be 1 because in our case, we remember this is a 2 output problem. The sum of these 2 will always be 1 coming out of softmax. Therefore, the target also will be summing to 1. So because this is 1, our delta 0 is what? Minus Y0 plus S0, okay? Or you can write it as S0 minus Y0. So that is the simple answer, okay? Now you can verify yourself. Can you guys guess what will be without me going into all the math, what will be delta 1? It will be S1 minus Y1, okay? So let me see if you further understand this, okay? So first of all, now if I take you back to our handouts, we talked about it last time. Like I said, even if it was a little bit intimidating, hopefully as we go through the example today, it will make sense. So we went through the same thing. Maybe I went it a little too quickly. But if you take a look, the final answer was, if we have the cross entropy loss, okay, what is the delta on page 3 in a softmax neuron? What was the answer? Si minus yi. So if it is for neuron 0, it will be S0 minus Y0. If it was neuron 1, it will be S1 minus Y1. Neuron 2, S2 minus Y2. So final answer was beautiful. So even though there are a lot of partial derivatives involved, but once you do it on a 2 neuron example, then you know, right? Okay, so of course, PyTorch library automatically will do this. But that is as I mentioned in the beginning of the course, we want to learn each concept exactly how it works. Once we understand it, we'll start using libraries, no big deal. Okay. So anyway, so the other clarification I'd like to make is so that you have a solid understanding of these things. Suppose you created a classification problem. And let's pretend the classification problem is a 3-class problem. Instead of 2, let's make it 3. Okay. At some point in time, coming out of the softmax, you have 3 outputs, A0, A1, A2. So somewhere here is the softmax, the last layer. Okay. What does that mean? There will be 3 targets. Okay. Y0, Y1, Y2. Okay. Let's pretend for a given training data, XY, because we always pick a training pair, right? Corresponding to this X, the target is 0, 1, 0. Okay. At some point in time, your softmax is producing, let's say, 0.2, 0.1, 0.7. Okay, this is the output coming out of the softmax. Okay, so my question to you is, there are 3 neurons, right? In our 3-class problem, at the output layer, there will be 3 neurons. So my question to you is, can you tell me the value of delta 0, delta 1, and delta 2? Based on our derivations, the target, like I said, is 0, 1, 0. So what is delta 0? What did we came up with delta I equal to? Si minus yi, correct? So let's go to the first delta 0. So Si, so think of this as, this is, remember, instead of, when I did the derivation, instead of A's, I called it capital S, right? So this is what it is. So now can you tell me what is delta 0? So this will be 0.2 minus 0, which is 0.2. Let's go to delta 1. This will be 0.1 minus, what's the target? 1. So it will become 0.9. Okay. What about delta 2? Points. So in other words, a simple way to understand it is whichever class is being recognized, whichever class is the target, we are going to subtract -1 from it. Okay. So -1 was subtracted because the target is 1. It doesn't matter what actual output it produced. For the others, we leave it as is because subtracting from 0 doesn't do anything. Okay. So let me see if you can see in the code as well. Okay, so somewhere over here, you will see in this code, I said delta 3 and I'm doing something range and then minus equal to 1. So y obviously is the target. Okay, so I'm subtracting -1 from it. The delta 3 equal to probs. And if you take a look at the probs, what does it look like? np.sum, exp scores, right? And exp scores is np.exponential. So you can see this probs is really calculating the output of the softmax, e raised power s plus e raised sum of all those, right? So as you get better in the programming with respect to Python, okay, in Visual Studio, what you can do is, suppose I give you a code and you're not, it's not making any sense, okay? What you do is you wanted to understand what is this delta 3 doing, okay? Put a breakpoint in this gray area. If you click, it will put a red dot, and that is called the breakpoint. Then what you do is you go through debug and start debugging, not start without debugging. So what we'll do is we'll run up to that and stop, okay? So first it shows me the 200 points that the data. As I exit out, the program will continue. So now once it turns yellow color, that means now it has stopped. If I put my mouse on delta 3, okay, in this example, there were two outputs, okay. So if you take a look at the two outputs, for example, do you see 0.39186? I don't know if you can read it. First one, right? Second number is point something 60, right? Two outputs. Okay. So 0.39 and 0.60, right? As we now try to compute the delta, like I said, what will it do? It will subtract -1 from those values where the target was supposed to be 1. Okay. So if I run it to the next step, so I put a breakpoint on the next step and I said debug continue so that it stops over there. Now, if I examine delta 3, remember the first number was what? 0.3 something. And if we subtract 1 from it, it became negative. Okay, the second number, did it change or no? So let me run it again. I'll stop it again. So let's go one more time. Okay, so before we compute the delta, I'll put this, this is coming out of the softmax. The sum of both numbers will be 1, and you can, the first number is 0.391. The second number is 0.60 something. So if you add them up, for sure it will be 1. So if your code has been written properly coming out of the softmax, we verify up to over here, right? Now let's pretend the target over here, the first output is supposed to be 1, second is supposed to be 0. So then what will it do? If it will subtract to compute the delta, 1 from the first output, so that 0.39 will become 0.39 minus 1. So that will make it negative 0.6 something. The second number should continue to say 0.6. So if we run it to the next step, and if I put my mouse on it, you'll see the first number became negative 0.6 and the second number stays the same 0.6, right? So that is how easy it is to compute the deltas. Okay. So now, hopefully as you do your assignment number 3, okay, I know if you're new to Python, there's a concept of classes and a few other concepts. There's NumPy involved. I'll just give you a few quick hints. Okay, in NumPy is the Python's matrix library. And it's very easy. For example, in the very top, you will say import NumPy as NP, so that if you say NP something, it will recognize, right? Now you can create some two-dimensional matrices as an example. So suppose you created M1 equal to NP.random. So random is one of the classes, right? And then what we do is we indicate the dimensionality. That dimensionality is referred in the technical term is called the shape in Python. Okay, so if you have a 3x4 matrix, we will say the shape is 3, 4. So when we create using NumPy something random, we can say, okay, give me a randomly initialized matrix with 3 rows and 4 columns. So this is how we will do, right? Suppose you do M2 equal to NP.random. And you wanted to test, can I multiply these two matrices, right? So the second matrix that I create, if I want to do M1 times M2, should be what? See, the first dimension has to match. Otherwise, it will give you an error message, right? So now you can say, suppose you wanted to do Z equal to M1 times M2, right? But in NumPy, you don't say dot. Like this, you will say Z equal to NP dot. The dot is the function that will do matrix multiplication. So now you can do, for example, M1, comma, M2. And if the inner dimensions match, you can, for example, in Python, say print Z. It will print all the numbers. Or you can say print Z.shape or put a breakpoint over here, put your mouse on it. It will show you, right? You can also do something like this in the beginning because gradually you want to get better and fluent in Python. Okay, so for example, let's say you wanted to simply test 2x3 with 3x2 matrix multiplication. Okay, you wanted to pick simple numbers so that you can verify, do it by hand and see is Python doing the same thing or not. So you can say something, you can create a list, let's say L1 equal to 2x3, 1, 2, 1, 2. Oh, let me do it again. L1 equal to 1, 2, 3, 4, 5, 6, right? And then you can say M1 equal to NP. Hey, I may be not remembering it correctly. Is it NP.array? But anyway, what you can do is you can pass the, I'll double check this one. You can pass the list as part of the NP dot. I know in PyTorch it is torch.tensor, and then you can pass it a list in. Okay, there is something over here. You can Google it quickly and test it. So where you can pass it a list. So now what it will do is it will initialize the matrix as 1, 2, 3, 4, 5, 6 like this, right? Similarly, you can initialize M2 and test it, print it so that you can do the calculations by hand and verify it, right? So, so as you do assignment 3, you'll see we are operating at the matrix level. We're using dot products, using NP dot to back propagate and so on. So anyway, this next week, your goal is to go through that code very carefully. Try if there's any confusion in any part of it, I'll put the link for the teaching assistant so that you can go, because I'm traveling this coming week, so I won't be in the office. But this next assignment is very important for your learning, right? So I'll stop at this point unless you guys have any questions.